We've waited the appropriate number of late minutes. So I'm very excited to have one of my closest collaborators, Sam Burke, come give the talk today. Sam and I actually started, we were going to do a project on optimal control. We were like, all right, first we have to write down the system. And then 3 years later, we wrote down the system and we found other stuff and never did the optimal control stuff. I'm very excited to hear what he has to talk about now. He's an assistant professor at University of Washington. Got a PhD from Berkeley. And wonderful to have you.
Cool. Thanks so much, Aaron. Thanks, everybody, for coming today. And thanks to Aaron and Matt Travers for inviting me and hosting me. It's been just a wonderful visit, wonderful day. So yeah, I'm happy to share with you some of the stuff my lab's been working on in the last couple of years. This is kind of an exciting tipping point for me. I'm in my 5th year of my faculty position, and now I'm able to present results that are all from UW. So no longer kind of carrying on stuff from grad school and postdoc. This is all really coming out of the group that I've assembled up at UW. Okay, so the overall motivation for the talk today is the unarguable observation that human interaction, our interaction with the physical world, is increasingly mediated by machines that learn from, adapt to, and try to assist our interaction. This is happening in a number of different domains. A couple of my favorite examples from recent years are robot-assisted surgery. I mean, this is now widespread. There are like hundreds of thousands of surgeries performed every year on like literally 1 million deployed units from Intuitive Surgical. Improves surgical outcomes for certain types of procedures under certain circumstances, but the future is bright for that area. In the middle, there's actually work that was done not too far from here, Andy Schwartz lab at Pitt, on brain-machine interface. So this is an example. Jan had a spinal cord injury, couldn't control, hasn't been able to control from her neck down her own body for a long time. And then by implanting an electrode array in the brain, reading out the electrical signals and kind of closing the loop, she's able to manipulate they describe it as a 10-dimensional anthropomorphic robot arm to do one of her favorite activities, an activity of daily living of independence that we all, most of us in this room, take for granted. Just being able to feed yourself on your own without assistance. It's really a remarkable thing. And then the final example, this was also work that was initially done here before Steve Collins moved to Stanford. Kind of highlighting the potential for not just mitigating disability or helping us when we have a disorder or an injury or disease or something like that, but actually just enhancing natural human ability. The really striking finding here was they were able to build a kind of fancy clutch spring mechanism to make a passive, meaning no power, no computer, well, no digital computer. Maybe it's a morphological computation, depending on your school of thought on that. But anyway, a passive mechanical device, unpowered mechanical device that improved the decreased the metabolic cost of walking for a population of people by 7%, something on that order. And you think, like, if you've never heard of this result, now you're at CMU, so you've probably heard of this result. But anyway, you think 7%, cool. But actually, if you think about the fact that one of the leading hypotheses about why we are bipedal is that we were made to walk long distances, basically outwalk our prey in order to kill them, it's pretty remarkable decreasing 7% with an unpowered device. And I think it just hints at the untapped potential to augment human ability, regardless of the ability level or the disability level that we come to the situation with. So I think this is a really exciting frontier of human-machine interaction. Obviously, within the scope of this talk, I'm not going to touch on all of these things. So let's drill down into a problem that I think is really interesting in this area, has potential relevance for each of these problems, but is kind of scoping it to be much more practical. The problem I'm going to talk about is robot teleoperation, right? So the picture you should have is that we have a person. That person's getting certain measurements taken off of them. The two that I'll talk about in that segment of the talk are manual, meaning joystick interface, and neural, meaning in this case EMG, so just measuring muscle activity through surface electrodes. And then those inputs are being sent to, processed by a machine. It might be remote, like on the other side of the world. It might be remote, like in the same room as you, but it's not like physically interacting with you. It's not physically attached to your body. You're not holding something with it or something like that. And then that machine needs to provide some sensory information back to you. Visual, haptic, maybe neural in the future, things like that. We've focused on visual up to this point. And just to put kind of a finer point on it, because robot teleoperation is a real big area, let's think about a really challenging task where this interaction needs to be highly dynamic and where I think in the near future the human has to be a part of the control loop. So something like fighting fire. So in the Northwest, especially due to climate change, but this has been a perennial problem for us, forests catch on fire every year. First thing we do is immediately send more people into harm's way, which is kind of crazy if you think about it. I mean, it's necessary, but wouldn't it be nice if instead we could send machines? But of course we know, and I know that this is totally cliche to show this video, I'm not going to dwell on it. We know that we can't send these machines to be fully autonomous in that kind of scenario. You don't want to rely on a fully autonomous robot at this point, humanoid scale, to go and fight your fires. And so my argument is that we should be injecting people into the loop to help solve this problem. Save lives in the near term. Long term, fully autonomous, but near term, why don't we have humans share some of the load? Of course, if we just naively sort of inject people into the loop, we can get really bad outcomes. A couple of fields where this is really well known, really well characterized. The aerospace people have been looking at this for decades, so work dating back to like the 60s, things like that, on what they call pilot-induced oscillations as one example. So as you try to make aircraft higher performance, you push their passive dynamics into a regime where they are marginally or even slightly unstable, because that increases maneuverability. And then what you do is you rely on the pilot in the loop, deep in the control loop, not in a supervisory level, not pushing buttons on an autopilot, but like hands on the, whatever they call it, joystick? No, they call it something else, whatever. In order to stabilize and maneuver the aircraft. But a phenomenon they discovered and have to watch out for whenever they design one of these things is the possibility that the neuromotor delay, so literally just the delay from humans seeing, taking in the visual scene and the display and everything like that, and then generating muscle commands to, perform the maneuver, correct for errors and things like that. That fundamental sensorimotor delay that you can't train out of people, right? It's just what it is to be a person. That delay injected into this marginally or slightly unstable control loop can itself cause instabilities. And if you fail to model that and take it explicitly into account, then you can crash test aircraft, which is what has happened in multiple cases. Usually not with loss of life, but loss of, probably the program manager's position when something like that happens. Another example where I think we're seeing this increasingly is enhanced safety features in cars or semi-autonomous vehicles, things like that. One vignette from one of the references, the second reference I have up there that I particularly like, in a study performed by an insurance agency advocacy group, so these are people on the side of insurance agencies, car insurers, found that in certain late model luxury vehicles, if you had paid extra to get an enhanced safety feature that would basically do lane keeping assist, it would turn on buzzers, flash lights when you weren't going out of your lane, statistically that year, maybe it was a fluke, but you were more likely to be in an accident. And so actually you should be charged more by the insurers if they're doing their job in order to have that quote unquote enhanced safety feature. Of course, this could have been a transient thing, statistical anomaly. It could be the kind of thing that we need to adapt to over time. Maybe probably people here where you actually get snow are familiar with if you have anti-lock brake system in your car, then you respond very differently to slipping than if you don't have ABS brakes in your car, for instance. So maybe there's a sociological adaptation that needs to happen. The point being that without taking into account, we can have bad outcomes. So returning to this picture, I want to inject humans in the loop with robots that are making and breaking contact with the world. So the fundamental question that's motivating the rest of the talk is how do we enable people to learn and control robots with contact-rich dynamics? I don't have a total answer to this question. This is just the overarching thrust and merger of research threads that are going on in my lab. But I'm going to talk about this kind of from the bottom up, talk about the robot mechanics, terradynamics, and from the top down, talking about how to what we know about and what we've learned about how people learn to control dynamic systems, and then the prospects for merging these two threads. By the way, you already know I talk fast. I have a lot of stuff that I'm happy to share, but I'm also happy to go slow, answer questions, have this be more interactive. You're welcome to interject at any time, especially Chris. So to start off, let me jump into this discussion of kind of bottom up, focusing on the mechanics of intermittent contact. So the first observation, if you've never thought about this before, again, you're at CMU, so this is unlikely, but anyway, if you've never thought about this before, is that the dynamics of legged locomotion, of contact, are fundamentally different from, in a certain specific way, from kind of classical continuous hydro and aerodynamics. And the key thing, whether you're a leaping lizard or a leaping robot, credit due to Mr. Johnson in the front here, Professor Johnson in the front here, whether you're a leaping lizard or a leaping robot, you primarily have control authority only in certain portions, certain phases or modes of your operation. And so you need to both be aware of that, and also your dynamics, kind of along with that, change very abruptly as you make and break contact with the environment. So as Aaron previewed, the way that we approached this problem of how do we control systems to do these things is first, well, how do we model these kinds of systems? And so the way that we approach this as kind of dynamicists, control theorists, was, it looks like there are multiple, it's a mechanical system, so at the end of the day, we're going to have, an x double dot equals something. But it looks like there are kind of different operating modes or regimes that we're switching between depending on which subset of the limbs are in contact with the world, with the terrain or objects or obstacles. So here's a mathematical model. Let's throw it out there. We're not the first to propose this, but what we worked very hard on for those 3 years from conception to delivery is exactly mathematically how to formalize this class of models and then derive some consistency and basic theoretical properties that make them like a somewhat reasonable class of models to start from. Just to give you kind of a flavor, because I will refer to pieces of this throughout this segment of the talk. We talk about some number of possible contact points. We enumerate the possible contact points. Simplistically, each limb could be in contact or not. Of course, at a finer scale, if I'm doing manipulation, it would be parts of a digit or something like that on a hand. Each of those limbs has a corresponding non-penetration constraint. It's basically, my fist can't go through the tabletop. We have, given a particular set of limbs that are in contact with the world, we have basically Newton's equations, but constrained Newton's equations, right? So we have these constraint forces that crop up depending on which subset J of my legs are in contact, and those forces point in directions to prevent penetration, so they point normal to the surface. And then we also, in order to make things kind of consistent and physically plausible, we need to prevent penetration to first order. These dynamics prevent penetration to second order. I won't accelerate into the surface when I'm touching it. But if I hit the surface with non-zero velocity, something has to change. That component of the velocity that penetrates the surface has to be dissipated. And so we adopt a convention that people have been going with for a long time, that perhaps that happens roughly instantaneously. And so my pre-impact velocity, q dot minus, instantaneously gets reset to a post-impact velocity, q dot plus. It might be, according to something that has this sort of structure, it's linear in velocity, nonlinear in position. It depends on how you want to model the impact, things like that. But that's at least a model, something to throw out there, kind of a starting point. Okay, so I want to talk a little bit more about the kind of dynamics these systems exhibit, because I want to give you some facts that we've derived about the theoretical properties, the mathematical properties of these kinds of dynamics. So think of the simplest system that you could imagine in this framework. I basically have a hopper. And so it has two masses. It's moving vertically in a gravitational field. There's some kind of actuator, spring damper-y thing with an actuator connecting the two masses. And if I drive this thing with a roughly periodic input, then I get a roughly periodic hopping motion out. And importantly, a way that I visualize the dynamics of these things, the trajectories, I start somewhere, some initial condition, position and velocity. And by the way, when I say initial condition in this talk, at the most basic level, I literally mean initial position and velocity. I also could lump in, for the purposes of all of the results I'm going to talk about, parameters like mass distribution, geometry, things like that, or even control inputs, parameterized, or sort of the whole signal as a function of time. I'm just going to refer to all of those as initial conditions, because I'm thinking very deterministically for the purpose of these theoretical derivations. So I start at some initial condition. I follow the x dot equals f Newton's equations for some amount of time. Eventually, some new constraint gets activated. My foot hits the ground. At that moment, part of my state, the velocity, is instantaneously reset to some new place, and then I continue as before. And now I'm in, really, from a certain perspective, a different component of state space, because now I have a new constraint active. My foot is on the ground, whereas before it wasn't. I also am going to be talking a lot about how these trajectories, how these dynamics vary as I vary initial condition. So again, in the vanilla case, initial state, but I could lump in things like parameters or things like control inputs, things like that. And they all have this basic kind of structure. In the case where I have just like a single constraint, so I'm just a hopping robot, there's just one foot coming on and off the ground. If I perturb in one direction, the red direction, or I perturb in another direction, the blue direction, things are going to evolve along. They're all going to undergo this jump. And so you kind of look at it and you're like, well, the way things vary with respect to initial condition is there's this discontinuity, which is true at the moment of impact, but it's not true away from that, like further ahead in time. So if I have a trajectory that undergoes an impact at some intermediate time and then reaches time t, post-impact, mid-stance, something like that, the perturbation to initial condition, say at apex, manifests as a continuous and differentiable perturbation in the final condition. This might be counterintuitive if it's the first time you're seeing it, but this is a really well-known result. First instance in the English literature we can find dates back to, of course, the Russians in the 50s. But people have, including ourselves included, have kind of rederived this result in various ways and forms over the years, so we're pretty sure it's true. But that doesn't tell us what happens. Very different things can happen if the sequence of contact activations and deactivations could vary. So for instance, if I'm a hexapedal Rex robot running with an alternating tripod gait, nominally 3 legs hit the ground at the same time, then the other 3 legs hit the ground at the same time, et cetera. Or if I'm a quadruped cheetah, doing a bound, then 2 legs and then 2 legs. But if you think about it, if I went and kicked the Rex, I know that would be cruel, but perturbed it, any kind of terrain variation, things like that, the exact sequence at which the limbs touch down or lift off is not going to be determined a priori. They're not going to happen simultaneously in general, and they could, in principle, happen in any order. So this led us down this path of trying to figure out what happens in these mechanical systems subject to these non-penetration constraints near places where multiple contacts are being activated, like along a nominal periodic gait of a multi-legged animal. And something kind of striking happens that's very different from what happened when there was only ever one constraint that could be activated or deactivated at one time, which is that if I'm dealing with a conventional robot, so something like an Atlas or a Minotaur, theoretically, what happens when I perturb away my initial condition in the red direction or the blue direction is that I end up in a different part of the state space. There's actually a discontinuity in the trajectory outcomes. So I literally end up in a different place, a different contact mode potentially, but at the very least my continuous state, my positions and or velocities are just not related in a continuous way to my initial conditions. Why is this potentially problematic? From a viewpoint of trajectory optimization or local search or path planning, you would like it to be the case that if I do a little wiggle here, I'll just get a little waggle over there. But this observation is showing that, in fact, you could wiggle a little bit over here and just get categorically different kinds of waggles and wuggles, or I don't know what I should call those. This is not our result. This has been shown in a couple different contexts. One set of examples is in the context of manipulation. Flavor of the result looks like this. If I'm a rigid robot hand, which of course my hand is not, but just imagine, and I'm manipulating a rigid object like this, stainless steel water bottle, then if I have some subset of my digits in contact, and then another one comes in and impacts at non-zero velocity, then the result is that some subset of my existing digits should pop off at non-zero velocity, and exactly which subset should pop off is determined by who I trust for my impact law. Do I trust Legendre? Do I trust Newton? Am I a Fourier kind of person? So that I find a little bit dissatisfying. That we need to impose assumptions externally in order to get sort of consistency in our outcomes. Another way this manifests is in quadrupeds. David Remy had a really nice result, I guess now a decade ago. If I could have a rigid quadruped, like a little dog type thing, doing a trot, then in fact there will be 3 gaits that correspond to feet hitting the ground at exactly the same time, and that's unstable. If I get perturbed off of it, I won't come back. And then 2 nearby gaits that correspond to the front leg hitting first or the back leg hitting first. So the point here is that these rigid kinematic trees, which are the common ways that we design and build our legged robots, yield these kind of shearing and ripping apart of trajectory outcomes. The key way that you can get, or a key way that you can get around this, at least theoretically, is that you need to remove the rigidity in the system. You need to remove the inertial coupling between limbs. Because mathematically, in our simple model, what's happening, and right, these are all statements about the models. Statements about the physical world is kind of a subsequent step. But if we formulate the simple model, I'm asking the question, what properties does the model have? It has the following property. If the limbs are rigidly coupled, then at the moment of simultaneous impact, if I were to first, to just hypothetically apply the front foot impact and then the rear, or the opposite order, I get different answers for what the post-impact velocity should be. And so then I'm in different regions of my state space. versus if I inertially decouple the limbs, so I put in spring dampery type things. I'll say a little bit more at the end of this section about exactly what kind of mechanism might be helpful. Then I get the same answer regardless of which order I apply the impacts in. So that the full impact law for the simultaneous case is just given by the composition in either order of each of the individual impacts. So we took this observation, and what it does to these trajectory outcomes, I'll kind of jump back and forth between these two cases. Right? If I have rigid legs with this inertial coupling, then I get these disconnected parts. I end up in disconnected parts of state space. But if I just make this modification that I enforce this mathematical kind of decoupling at the moment of impact, things come back together. They come back together to become continuous, but kind of interestingly, in general, they're no longer classically differentiable. So that's indicated graphically by, blue and red initial condition perturbations lie in the same subspace, the same linear subspace. So if in the case where trajectory outcomes were differentiable, then they would also lie in the same subspace. That's what being linear means. Here we have continuity, but not classical differentiability. We have a certain kind of piecewise differentiability. There is a first order approximation of if I get perturbed in red direction initially, where does that lead me at the final time? And similarly for blue, but they don't have to satisfy linearity like if I flip the sign on the direction. So these results came out in kind of a couple of different papers. We laid the groundwork earlier on in this paper that's not about mechanical systems, but about just non-smooth dynamics, vector fields. And then with me and my student, we're able to kind of extend these results to these mechanical systems, subject to unilateral constraints, so that we get genuinely piecewise differentiable trajectory outcomes. OK, so now I have continuous variation and piecewise differentiable, which is going to be useful in a bit. But a natural question arises, OK, so things aren't like shearing apart into different places, but are things getting closer together, or are they spreading apart? Right? So the question is, are we expanding, or are we contracting in time? It would be nice, the nice thing would be that we're expanding in every direction all the time. That's a very strong property a dynamical system could have, but it's a desirable property. If my mechanical system had that, I could dramatically simplify problems of planning and control and things like that. So this was the problem that we kind of zeroed in on as an application of these theoretical tools. Really quick aside, before I can answer this question about expansion or contraction, I first need to tell you a little bit about what I mean by distance, because it's not, given that we're in this hybrid, piecewise defined, different contact modes world, the notion of distance gets kind of funny. So the way that we formalize distance comes from the following kernel of the idea. I have two states of my system. I have the hopper right before the foot hits the ground. So the foot's like reached zero height and has negative velocity. And then according to my model, at the same continuous time instant, right, there's going to be this instantaneous reset where that foot velocity is going to go to 0. Now those are two different states of the system, and there was a state transition, a discrete time state transition that related them. But because they literally, those states occur at exactly the same time, like continuous time, what if we just do the violence of saying, you know what, for the purpose of like comparing where trajectories are and where points are on trajectories, let's just say that those are the same point. Those are at zero distance from one another. This is a pretty wild, kind of a little bit of a radical assertion to make. This is going to dramatically change the topology and the metric properties of the system, but something we worked out. OK, so this is the one admission that this happened while I was in grad school. It's not from UW, but I just think it's such a cool result, and it's kind of central to being able to understand the subsequent thing that I want to just briefly describe it. We puzzled out that actually you can make this assertion, and in a reasonable class of hybrid systems that includes these mechanical ones that we're talking about, that assertion leads you down the path, if you want to kind of consistently extend it to a distance over the whole state space, to a distance metric. And the distance metric makes a certain amount of sense, at least in the sense that it's compatible with the quotient topology for people that are familiar with that kind of terminology. If not, I just said blah, 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 blah. I have a distance metric, is the point. And it's a distance metric that, importantly, pre-impact states that map directly to a post-impact state, those are at zero distance, even though the velocities are different. Okay, that's my assertion, and mathematically, I can make sense of that. So now I want to get to this question of, do distances shrink, i.e. contract, or expand in time? And the approach that we took was to look back at this technique that had been fleshed out for smooth nonlinear systems. There are many different references. Actually, this dates back to, unsurprisingly, the Russians, Dimitrov, things like that in like the 60s, physicists thinking about this. But one of the seminal references is this low Miller-Slotin, so just to have a pointer if you want to take a look at this stuff. And the flavor of the results is the following. This is not the full generality of all the different variations, but this is like the flavor. If I have a continuous time system or a discrete time system, so if I have a smooth vector field, x dot equals f of x, or a smooth difference equation, x plus equals r of x, and this can depend on time. That can be time varying. And if the dynamics are what's called infinitesimally contractive. OK, so what are these conditions saying? One is an eigenvalue condition. The maximum eigenvalue of the symmetric part of the Jacobian of the vector field is less than 0. What is this trying to say? I take my dynamics, my nonlinear function f, I take its derivative with respect to state, I get a matrix. Is that matrix like shrinking stuff or expanding stuff? One way to measure that is by looking at eigenvalues of the symmetric part. OK, if it's shrinking stuff, that's the condition. In the discrete time case, it's a little bit easier to think about because it's just saying, oh, the maximum singular value is less than 1. That just means that to first order, the map's a contraction. That one's a little bit easier to think about. In either case, you can get a constant c. You can show that all trajectories converge toward one another at an exponential rate. So you can find a constant c that makes this kind of inequality hold. Again, this is a really, really strong type of stability a system could have. Not all systems obviously have this. There are some sorts of converse results, but I'm not going to really get into that. Very strong ask, but if you had it, it would be nice. It means that all trajectories forget their initial conditions. It's kind of nice. Now, if we want to generalize this to our current setting, right, we can't just apply the continuous time result or the discrete time result, because fundamentally they interact, right? When I apply my switch, depended on when my foot hit the ground, which depended on the forces that I experienced as my foot was in the air. And so we need to somehow combine these two things. Really quickly, this is mathematically the most technically dense slide, but just to give like a flavor of the idea, we look at how perturbations vary, like the size of a perturbation off of a trajectory varies in time. And the key insight is that around the time of the discrete time switches, the resets, you need to consider the interaction between the continuous time flow and the discrete time reset. You can't just look at the derivative of the reset map alone. So you need this special modified matrix. It has in it the derivative of the reset, and then it has a bunch of other information about the continuous time dynamics in kind of a close region, and the geometry of the guard given by the derivative of the normal vector to the surface of that. Sorry, I said guard. Constraint surface, the switching surface. This is called, just for people who really want terminology, this is called a saltation matrix in the literature. Turns out to be the right object. All of that to say, we have a way to get contraction-like flavor of result in this mechanical setting. Of course, naturally, you're going to need contraction not just in continuous or discrete time alone. You're going to need it in both. And so we say, if you're contractive in continuous time and discrete time, but the discrete time contraction condition is with this modified saltation matrix S, it's not in terms of just the derivative of the reset. We need this extra information. Then we get the same kind of all trajectories converge toward one another at an exponential rate. This is in terms of my distance metric. If you chose any other distance metric that was qualitatively different, this would not be possible. We do have like a necessity result, almost a converse in that sense, that shows that if you want to be contractive with respect to our metric, like you have to have these properties. And then the last thing I'll say is, using this result, what kind of limb decoupling do you need in order to have this kind of contraction thing happening? So rigid, definitely not. Right? We knew that because we don't even get continuity, so we're definitely not going to get this kind of continuous and infinitesimal contraction. Surprising to me, it wasn't enough to just put a spring damper. So to like inertially decouple, it wasn't enough just to put a spring damper. The reason being that dampers, at least in my simple-minded electrical engineer conception of them, are physical elements that if you change the velocity, then they respond instantaneously. So like when my foot hits the ground, it changes its velocity. So then the time rate of change of the leg, the leg length, changes discontinuously. So the force changes discontinuously. That discontinuous change in force violates our saltation matrix condition. So that's a no-go. No-go just from the perspective of our theory applying. Okay, you could still have a perfectly reasonable, stable system with this kind of leg, but just turns out our theory didn't apply. What we needed to interject was what's called a viscoelastic spring damper, which basically just adds a spring in series with the damper to smooth out make that force transition continuous instead of discontinuous. OK, so that was the whirlwind tour of these contact dynamics and the kinds of theoretical results we've gotten on them. Any questions before I completely switch tracks, please?
Please hold for when the mapping is piecewise, like you had mentioned before.
Yeah, so this, yeah, exactly. This fact about, actually our paper is about hybrid systems specifically, but then we apply it to mechanical systems in examples. Yeah, and this is, sorry, I forgot the exact phrasing of your question. Oh yes, sorry. This applies when the trajectory outcomes are piecewise differentiable, continuous and piecewise differentiable. Yeah. Cool. Any other questions? Please.
Are there any energy arguments we can apply? We know things like rigid body systems with no springs and dampers are mutually stable. Does that allow us to say things about volumes they can occupy or something like that?
Yeah, great. So the question was, does considering energy in a mechanical system inform this in any way or kind of augment this? So it was actually exactly that consideration that led me to the intuition that the middle category here, just a spring damper, ought to be contractive in this way because the continuous time dynamics on their own are dissipating energy, if it's a spring damper, are dissipating energy at all times. The discrete time dynamics on their own are dissipating energy. And so why when I shove them together, why wouldn't I get a nicely contractive thing? Now, I'm certainly still getting a stable thing where energy is not increasing in time, and in fact, it's decreasing. So OK, if I wasn't actuating the system and I just dropped it, of course, it's just going to settle into on the ground and just kind of at its equilibrium position. I'm interested, though, in the case where I'm actually periodically exciting the thing. And so I'm injecting energy into it. In that case, the simple use energy as a Lyapunov function argument doesn't apply because it's a time-varying system now. Basically, what we're showing is that if what you want, which is a much stronger kind of stability than simply I want things to converge to one steady state, if you want that all perturbations contract uniform, at every point in space and every instant in time, no matter what, then you need this kind of additional viscoelastic decoupling in this mechanical system. Without it, there are perturbations that, to first order, for a small amount of time, get amplified through the impact. That's not to say they increase energy. It's to say the size of the perturbation increases through impact. Yeah.
So if I have a single leg hopper that's perpendicular to
Yep.
small perturbations will cause it.
Oh, sorry. In this, so the question was about these vertical hoppers. Could they fall down left or right? All of the examples, all this discussion I'm giving, these hoppers are constrained vertically in a gravitational field. So imagine they're on a rail. I'm not talking about something moving through the plane or kind of overground or something like that. I think we plan to apply this to an example, like a multi-legged example. We haven't done it yet, so I can't report on the result. I think it should apply, but yep.
Yeah, I guess my question, you may address my question
Yeah.
in the second part, but I want to ask it first.
Please.
Because if you use the carbon limbs, then you have the zero elasticity in your limbs, and you reduce your control bandwidth.
Yep.
And you introduce additional nonlinear parity, and also, I guess you also need to augment your state by adding the length, even velocity of these additional mechanisms. So
All good points.
yeah, even you solve the discontinuity problem in this aspect, you introduce additional complexity.
Yeah.
How do you?
Yeah. So OK, the observation is the following. Here's a nice thing about rigid robots. Because they're, by nature of being rigid kinematic trees, they have fewer degrees of freedom overall than if I just took the degrees of freedom of each individual segment and then added them all up. Why? Because of Nether's theorem, right? The total degrees of freedom of the constrained mechanism is equal to the degrees of freedom of all the individual segments added up minus the number of constraints. And with rigid systems, link A is constrained with respect to link B. As soon as I decouple, so that's a nice thing about them. bad thing about them, from a certain perspective, is these theoretical properties I was describing, that you get this kind of splitting, shearing of trajectory outcomes. Maybe that will make optimization hard. Maybe that will make planning hard. This sequence of observations is if I decouple the limbs, so I put in some squishy stuff, automatically I blow up, and now I have lots of degrees of freedom again, as well as, I'm toying, here my toy models are simple, linear, spring dampers, but in reality you put in this series elasticity and it's all nonlinear and it's nasty and whatever. So I get additional nonlinearities and I get many more degrees of freedom. That's the price I would have to pay in order to possibly have a mechanical system that has this contraction property. So I do not have a proof of concept robot design or even a cartoon multi-legged robot video to show you. But I don't know. I don't think there's one answer to where should you be on this trade-off curve. But you're absolutely right that you're paying a price to go down this path. Yep.
To kind of continue that, is the point of this to say we should be focusing more on kind of elastic or viscoelastic materials and robots, or we can still, this is just a different analytical tool to resolve some of these, but we can still learn things about these models that would still then apply to the system.
Yeah, so the question is whether, I'm having trouble summarizing the question.
Would the results from this...
I'm trying to do it for the recording. You said it very nicely.
Or would this say you should change your design or change your model?
Fair enough. Yeah, so do I want to change my design or change my modeling paradigm? Yeah, I think a bit of both. A couple of observations. One is this is mathematically, if I want to have mass in the foot, the easiest way to get this kind of decoupling thing to happen. Another way, mathematically, although possibly less plausibly physically, although possibly not, to get this decoupling to happen is to make the limbs super light. If the limbs are super light, then even though formally speaking, because they're like a minotaur, one rigid limb is technically rigidly coupled to another. In practice, like we've tried to find this in experiments, we tried to see the effect of this coupling, and we just can't even observe it. And so perhaps for other kinds of actual rigid kinematic trees, changing the inertia distribution gets you close enough to this property that you might still be happy. So I guess I think of this result as kind of, this set of results as kind of saying, look, if you want these desirable properties, then your mechanical system has to have the here are the hopefully it's necessary, but at least sufficient conditions a mechanical system could have in order to have these nice system level properties. Cool. Yeah, another question?
So it seems like one of the core assumptions here is that you know that all of these contacts will happen. You don't know necessarily the sequence. I guess first, is that a fair assumption to make? And how much more difficult would it be if you were to say, know that it's possible to have like your front foot hit down, and before your back foot has a chance to hit the ground, you've already sprung off again?
Yeah, it's a great question. So the question is what type of constraints and to what extent do I need to constrain the sequence or family of sequences of constraint activations and deactivations in order for these results to apply? So one nice thing about these results is that if I know that I have, I have 4 legs that are going to touch down and then eventually lift off, then under these appropriate decoupling conditions, I can continuously and piecewise differentiably vary between possible sequences. So that's nice. However, if I wanted to kind of continuously go from 3 legs touching down and leaping off to, okay, yeah, I'm going to include that 4th one. There is a technical obstacle that I haven't been able to get around, which is grazing. It seems like in between leg off and leg on, if you kind of continuously connect the dots, there's necessarily going to be a point where your leg scuffs. And that is problematic for some of these results. Yeah, so think about so here's a pendulum. And then as it gets closer and closer to a surface, then eventually it scuffs. So I don't know what it does. Does it stick? Does it slide? That depends a lot on friction and the level of detail at which you're going to model the geometry. But in order to go from hitting the ground for sure to not hitting the ground at all, seems like there needs to be some intermediate point where they scuff, and scuffing is annoying, to say put it mildly. So, so I don't know, I can't say theoretically that we could say search over all possible gates with this, continuously vary over all possible gates while maintaining these properties. Cool. Any other questions? Well, you fulfilled my wish. This has been highly interactive. I've burned almost all of my time on the first, not half, but like 2/3 of my talk. I don't want to, I'm not going to impose on your schedule. I'm not going to make you stay here for another half hour. Do you want like the flavor of the human in the loop results? And then we'll go to questions? Cool. Thank you for indulging me. At least the few people. OK, my host. My host encouraged me. OK. Thank you for indulging me. OK, so the way that we approach this human in the loop problem is we really put them in the loop in like a very classical control theorist kind of way. OK, so I look at this teleoperation problem. And this goes back, again, decades. This McCruer gang have been looking at this in the aerospace land for a super long time. And we're kind of just building on this very well-established body of work. Here's the kind of remarkable thing. Humans are nonlinear. Sorry, that's not the remarkable thing. Of course we're nonlinear. We contain multitudes, right? Humans in the loop can be linear. So what was really found, like to me, the striking finding from this work decades ago is that if you put a human in a cockpit and you give them a trajectory to track and you give them a linear system dynamic to track, that's the M, then with respect to the reference you're trying to get them to track and the error that they observe on the screen, they will respond very much like an LTI system. Cool. Like, we know a lot about LTI systems. We know how to measure them from data. We know how to predict how they respond to things. We know how to control with them in the loop. We can handle uncertainty in them. That's the paradigm that we're working in. Not because we think that everything in the world, all the machines in the world are linear. Of course, I want to mesh humans in the loop with contact-rich dynamics where things are highly nonlinear. But I think this is a remarkably powerful kind of test case to learn as much as we can about how humans control systems, how they learn to control systems, how they adapt in response to adaptation in the systems they're learning to control, so that we can take those findings and at least hypothesize, have guesses about how people will respond when we're doing that with a firefighting legged robot in a wilderness setting. Okay, so that's a bit of a bridge to go over, but that's our starting point. The kinds of cool things that we've done. Here's a reasonable hypothesis. The way that people process references, like where they want to go, and errors, the difference between where they are and where they want to go, is they use a little bit of both, right? I look at where I want to go. We give them a little bit of preview. I look at where I want to go, and I use that to inform the input that I'm going to apply. But I also look at how much error I presently have, or maybe the recent history of that error, and then use that to affect how I'm going to apply it. Reasonable hypothesis. The previous slide was about how this is well connected with like the neuromotor control, kind of the science of how we think people control stuff. The cool thing is that in this, plausible that we have both of these mechanisms, feed-forward, feedback. There are plenty of experiments from the neuroscience community in very nonlinear tasks that demonstrate the existence of these different pathways. What's cool in this linear system setting is that we're able to easily estimate from data through non-parametric system ID, just frequency domain-based methods, each of these elements, and then kind of analyze them in different settings. The way that we estimate them is just with block diagram algebra. I'm not going to dwell on it, but I just think that's exciting that the stuff I teach undergrads is like totally a key part of this research. And the upshot is that, yeah, people learn to invert system models. So like I'm learning to fly a quadrotor and I'm commanding velocity. I basically learn the relationship between that velocity and the quadrotor's motion. And then in order to get it to follow a trajectory, I look at the trajectory, I differentiate it, and then I apply that as my input. Roughly speaking, a little bit attenuated, right? So the dashed is it would be the exact inversion, and the humans are always kind of seem to be hedging, kind of not quite, maybe being lazy, depending on your perspective, maybe being conservative or safe, not quite exactly achieving it. That's true for first order system, second order system if I'm commanding acceleration. Here's the new result from the group, and I'll stop here after I just give you the result. We looked at how does the interface affect these results. Right, so if I was using a manual interface, that's conventional. But what if I'm using I'm going to call it neural. That's a little bit of a reach. EMG, okay, so surface electromyography for biceps and triceps, or deltoid. No, I think it's biceps and triceps on the picture. How does that affect the results? So super easy to measure the feedback controllers, super easy to measure the feed-forward controllers, and then compare them in these two treatments. And the result I got the year wrong, but my student just got her paper accepted to CHI, this year's CHI, which is a big win. First time we're going to go to that meeting. And one of the coolest results there, in my opinion, is in this comparison. So if we look at tracking error or inversion error, so if we look at how well people do at actually tracking the reference signals, or how well they invert the machine's model, then we see no differences in tracking error. We see no statistically significant differences in tracking error for first or second order systems, or in inversion error for first order systems. But then we see this big difference in inversion error. So basically, our interpretation is how well people internalize the dynamics, or are able to internalize and use the internal model to generate reference controls. They do a much better job with the EMG interface. Why? I don't know. It's interesting. Love to hear people's hypotheses. I mean, one thought is that in order to generate manual motion, my muscles first had to be activated by an EMG signal. And just statistically, EMG seems to have higher frequency content. And apparently, people can modulate that higher frequency content. That's where we see most of the improvement. So this is kind of a provocative idea. If I want to fly a quadrotor through trees, then manual may not be the best interface. Maybe I want EMG, or maybe I want a combination of the two. And so we're looking at using these methods to kind of explore that interface. Well, thank you for indulging me. I'm going to skip past a bunch of very mathematical slides. I'm happy to go back to them at any point if people are interested in them, online, offline. So we're aiming, for doing kind of experimental integration of these two different aims. So with that, I'd like to acknowledge the contributions of all my collaborators, funding agencies, and thank you so much for your time. And I'm happy to take any other questions people have. Of course, you're welcome to leave anytime you need to or want to.
For the first question, I should announce, after this, there's we have a room reserved to sort of continue talking with Sam and answer more questions and go to whiteboard or anything like that. So if you didn't get your question, or if you wanted to ask for more detailed questions, please join us afterwards.
Or if you really want to see those slides.
Yeah. Let's get a couple more questions.
Perfect. So I see Chris, yeah.
So if I'm an animal trainer, the easiest thing is to train animals to do stuff that's very close to something they do naturally.
Uh-huh.
And in psychology, there's this guy Gibson, and he talked about ecological stuff. It basically boils down to don't try to get people or animals to do weird stuff. Similarly, maybe this boils down to, or should be replaced by the statement, try to get people to do behaviors that are very similar to behaviors that they encounter in their everyday life or natural behaviors, and hang a machine off the other end and you'll get good performance. And to the extent it's some weird thing that they've never done before, you'll get crappy performance.
Interesting hypothesis.
So, in the movies about training astronauts, there's always a scene where they put them in the, rotate them at high angular velocities in all sorts of directions, and ask the question, can they still fly the thing, without passing out or throwing out balls? And that's of course one example where you're sort of asking them to do things they never encounter in real life. And very few people are good at it.
Well, I mean, arguably, all we do all day in universities is get people to do things that they don't do in their everyday life, or wouldn't otherwise be doing in their everyday life.
They're terrible at it. Another example where you ask people to do things that is very abnormal is martial arts. So you ask your average person who's from here to there, they make a nice symmetric velocity profile. In martial arts, you don't necessarily want to make a nice symmetric velocity profile. And it's hard to train people to do that.
Yeah, and in general, my understanding, not that I don't have any personal training, but just chatting with people that have gone down that path, my understanding is part of the game is moving in statistically novel ways. So being unpredictable, right? So meaning not sequencing your moves in ways that are typical or anticipated or kind of similarly. Yeah. Yeah. Am I correct in inferring that part of partial motivation for your observation is, I'm potentially asking people to control firefighting robots that I'm not imagining that they have to be anthropomorphic. My ideal firefighting robot might be a box with 5 limbs coming out of it, each of which has a different attachment on it, and then its body cavity could fit a human, or it could be filled with fire suppression chemicals or something like that. And so telelocomoting, teleoperating that is going to be highly non-intuitive, not part of the daily life.
Okay, there are 2 corollaries. One is don't build giant spiders. Howard's here, I hope he hears that. The second is put the pilot in the vehicle.
Okay.
Don't try to get them to do it remotely.
Sounds dangerous.
Pacific Rim was right. If you want people to fly these big robots, you gotta put them in the robot. They gotta feel the thing.
Fair enough, fair enough.
Now, he's suggesting we could fake it all with force feedback. I
Yeah,
don't think so.
interested.
In the DARPA Robotics Challenge, the biggest problem was human error, and the reason there was so much human error was the human was cut off from the robot.
Lack of situational awareness.
They just, it was so, this impoverished little, trickle of data. And you gotta get people out there doing normal behavior.
Interesting.
Certainly not.
Yeah, so force feedback can be great.
You're an optimist. I've been hearing people talk about force feedback.
I think we have another question.
Yeah, I have a question for Chris.
See ya.
What does putting the person in the robot accomplish that having the person remotely located doesn't?
Why are videotaped classes so boring? What's the difference between watching, videotape's the wrong word, a recorded class versus being in there? From our engineering point of view, there's nothing. But clearly there's this huge difference in immersion and engagement.
What about video games?
I hate video games. They just don't turn me on.
Certainly for space robotics,
Well, should you really have the human fly the vehicle? Well, this is just
This is
a
a
damn
great
vehicle.
discussion for the discussion. Let's try and get maybe 2 or 3 more questions. We got a couple minutes here. Any questions for the speaker? Yes.
Contraction seems like a very strong property.
Contraction is a very strong property. Can confirm. Mm-hmm.
I was wondering what kind of assumptions is your standpoint do you think that is such a strong property that we might have to relate to I think the more realistic.
Yeah, this is a good point. So contraction is a very strong property. I do want to note, which I didn't have a slide on, that because the dynamics can be time varying, you can have, for instance, you could consider it an open loop, or to connect with the second part of the talk, a feed-forward input. That means that all trajectories are converging to one another at an exponential rate. What they're converging to is not an equilibrium. It could be, if the input is periodic, then it could be a limit cycle, a stable gate. Or if it's aperiodic, then it could be whatever it is. I'm doing a cartwheel, somersault, backflip, scaling the rock wall, something like that, theoretically. I mean, that's a big ask to have that big of a contraction region and find the input that does the thing. But I just wanted to make the point that one thing I like I find appealing about the contraction theory, in contrast to Lyapunov stability theory, other kinds of things, is that you can get convergence to a non-stationary or an aperiodic behavior or potentially maneuver. The corollary of that that has been exploited in the classical, meaning like for smooth nonlinear systems contraction literature, is that to a certain extent you can decouple, if you want to go down this path, you can decouple trajectory generation, like planning, and stabilization or trajectory tracking, so feed forward and feedback. Now again, maybe that's not the best thing to do. I'm not saying it's universally the right thing to do, but it does have a certain appeal. that maybe it's going to be easier to learn or generate a nominal trajectory from one initial condition that you like, and then just make the system contractive so that all the other trajectories will follow it, than it is to synthesize a policy over the whole state space.
But it's the contraction that I don't quite follow, because I can see for a real system that maybe is validated without output.
Mhm.
The contract, like the one-legged hopper example, if it falls to the right or the left, that's definitely not contracting. We still want to really find policy for stuff.
So in the hopper example that I gave, it's constrained. It's like on a vertical rail.
And that's what I was trying
Yeah.
to say.
If I had a multi-legged robot, so here's my imagine the robot as a sphere. So imagine a robot that is a point mass or a spherical body, and then these viscoelastic limbs radiating outward from it with point mass feet. Then almost directly, I can say that if you had an actuator in each of those limbs, like a prismatic actuator in each of those limbs, and you drove them all with some periodic input that had the same period for all of them, could be a different input in each leg, but periodic input, I can pretty much tell you that you're going to get a periodic gate out. I have no idea what it's going to look like, but the fact is that this property that all trajectories are converging toward one another, so that if you knew any particular trajectory that you got from one particular input and one particular initial condition, that's what everything is going to end up doing. That's the path toward like a whole robot behavior.
Now, is it going to converge up to a phase, or is it also a phase?
Oh, this is a great point. So I can't have, in a contractive system that is not time varying, there can be no limit cycle. So there is no internal phase to a contractive system. But if I have a contractive system and then I have a periodic input, it's the input's clock that determines the phase of the gate, say.
All right, let's take this video.
Cool. Thanks so much.